Hello, welcome to Chapter 5, Section 2, Properties of Quadratic Functions in Standard Form. Let's do an application problem. There's a really cool picture in the book of a speedboat. An inboard speedboat, not an outboard speedboat. And my area of expertise is not in engines. I mean, I know how to change oil and I know what two-stroke versus four-stroke means. But I have friends that are engineers, and some of them work on airplane engines. And I actually have a friend who works for Polaris who works on, what do they call it? Not like, it's the high performance ATV. I know they sell Rangers, but it's whatever their like really sporty one is. You're probably screaming at me right now saying it's this. I'll have to look it up later. Okay. But this one kind of serves our purpose here. The power measured in horsepower generated by a high performance engine is based upon how many revolutions per minute of the engine. And revolutions means how many times the crankshaft turns. Okay? And this is where I was trying to think about how much background information do I give you with this. So what you might want to do is just Google and see if you can find like a GIF or a GIF. I'm not going to get into that argument of like how an engine works. And in a typical gas-powered engine, gas combustion engine, the crankshaft is driven by pistons and how many times the crankshaft turns around, which for a car will actually gets connected to the wheels via the transmission. Or for a boat, there are transmissions in boat, but sometimes it's more direct, like in older models, I suppose. So you just like turn it down and turn down the power, and you go less speed. But anyway, that's what I'm trying to explain. The revolutions per minute, the RPMs. Maybe you've seen that in your car. There's a monitor in the dash that says it's the tachometer, and it'll say the RPMs of your revolutions per minute of the engine. That's the crankshaft. It can be modeled by this function. All right, let's get to it. It can be modeled by this function. P of R, the horsepower based upon the revolutions per minute, is negative 0.0000147 R squared plus 0.18 R subtract 251. I'm guessing that Dr. Berger has a friend who's a mechanical engineer, and he borrowed this from his engineer's friend. Okay? So, I'm guessing that's where it came from. And this is where one of these situations where if the numbers are really, really awkward, and these are very awkward numbers, that means that it's probably a real world problem, because in the real world, it's not nice and tidy. That's where we mess up. In Algebra 2 and Algebra 1, we give you nice, tidy problems instead of real problems. The question is, what's the maximum horsepower of this engine? What is the maximum power of this engine to the nearest horsepower, okay? And how many RPMs do you have to be at to get there? Okay, now, if I graph this, I'm going to show you how to graph this. I'm going to go to y equals negative 0.1234147, and I have to use x squared plus 0.18x subtract 251. My graph, whoops, I forgot I had another graph in there. Hang on, it's got to load. Okay, I got to turn this one off. All right. And let's see if I can do a good table here. So I'll do 0 to, I don't know, 10. And actually, that's not going to work. let's do 0 to 10,000, and let's do 0 to 400. Maybe that might work. Yeah, okay, that's going to show in my graph. All right, cool. I can see more of it, but that's okay. So like right here is going to be the maximum. So my X value is the RPMs, my Y value is the horsepower. It's going to increase horsepower until it starts to decrease. All right, so I want to find out that point right there. Okay, so my axis of symmetry is going to be B, which is 0.18, divided by -2 times A, which is -0.0000147. Let's do second quit. Go back here. 0.18 divided by, yeah, I'll do it this way. I got to do parentheses because you got to multiply first. -2 times -0.000147. All right. Now, that, hang on a second. I think I forgot a decimal place. Okay, I'm going to try it again. 0.18 divided by -2 times -0.00000147. Yeah, okay, I forgot. I don't think I put enough zeros the first time. Because this is going to be approximately 6,122. Now here's the cool thing. You can go ahead and estimate it, but you can do something else. Check this out. See that STO? I can store that answer into my variable. Now it tells me that whenever I hit X, it's going to have that value. That's going to help me because the next thing I'm going to do is I'm going to take that and put it back in the function. So -0.0000147 times x to the second power, and that x is that number that I found out, plus 0.18 times x, subtract 251. That's about 300. So, if you remember my graph, there's my graph again. I have, and because that's negative, I have a maximum, and my maximum horsepower is 300 at about 6,122 RPM. And that's a pretty powerful engine. 300 horses running at over 6,000 RPMs. And you're going to lose some of that, probably due to some physics that we haven't talked about, if you go faster than that. if the RPM goes faster than that. Okay, now I hesitated to do this problem, but I wanted to show you to not be afraid of problems that seem to be real problems, that seem to be complicated, but you can do it. There's nothing in this that you didn't know how to, and even if you didn't have one of these, yeah, you'll probably need a calculator, okay? You don't have to have a TI-84 or something like that. You could probably figure that out, okay? I don't think we're going to have anything that complicated on any assessments, but I wanted to show you how to do it. Bye.